All right, pre-calc, we're back for part 2 of 1.1. I totally misread what this question was asking you, which is actually a pretty good skill to know, to be able to kind of like maneuver through textbook course material. So, I was trying to create a bunch of ordered pairs in which we needed to use this distance formula between, but they were making it so much simpler. What they're saying is that these are coordinates on a number line not in two variables, not on an xy plane, but just like on one number line. This is good news because it's way easier. All you have to do, so I'm going to erase this first. Bye. And then write a number line that says, okay, point A, B, and C are, let's just say 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's -9. There's 1, and there's 2, 3, 4, 5, 6, 7, 8, 9, 10. They're basically just saying, find the distance between A and B. That's like taking the absolute value of 1 minus -9. Yeah, bigger number minus the smaller. It doesn't matter which order you do. That's 10 units. So, part A, for number 17, given these coordinates, the distance is 10 units. Does that make sense? So BC would be, what's the distance from 1 to 10? Which would be 10 minus 1 is 9 units. CB would be from 10 to 1. I guess they're just saying like, hey, we're putting distance as it's always just the absolute value of those. So it's going to be 1 minus 10, absolute value bar, doesn't matter. That's also going to be 9 units. And then when you go all the way from A to C, A was our -9, C was our 10. That's going to span 10 units here, 9 units here, add them together, and you get 19. All right, so luckily I made the discovery that I was way overcomplicating this. So please disregard the last part of that video in which I pushed you in the wrong direction. All right, next example I would like to go over is number 25. So in number 25, they're trying to get you guys to, again, rewrite the expression without using the absolute value symbol. And so they're saying x is always going to be less than -3. So if you see something like that, I would say, let's play around with it by plugging in numbers that are actually less than -3. So if I took the absolute value of 3 plus -4, I am going to get 3 minus 4 inside here, which is -1. Absolute value of that is positive. So it's kind of like 1 is going to be our, almost like a bottom integer value. And, oh, wait. No. Here's what we got to do. You can test numbers all you want. But there's a fundamental aspect about absolute values that I'm really going to talk about in the next chapter, but since we're here, we can deal with it on a little tiny measure right now. Here's what I mean. Absolute value functions, if you remember all the different types of graphs that your previous math teacher talked to you about, absolute values tend to look like V-shaped functions. It's like a line going this way and a line going this way. That's because it's taking x plus 3. So let's say it's, okay, so at -3, everything flips around. So when you're going starting point at 3, the slope of that line is a 1 in front of the x. So that means you go up 1, right 1, up 1, right 1. Or down 1, left 1, down 1, left 1, down 1, left 1. Yeah, it looks like this. This is everything that's bigger than -3, the behavior of the graph, This is the behavior of the graph, everything less than negative 3. So I guess what it's saying is, what does this thing look like when we take away the absolute value bars? It's like saying, hey, the absolute value bars creates this V shape. If I took the absolute value bars away and wanted to just look at the behavior left here, so it's like saying, forget everything that's greater than negative 3. All right, I'm forgetting everything that's bigger than negative 3, negative 2, negative 1, 0, all that's bigger than negative 3. What are we left with? We're left with a linear equation that, if extended further, is a line, okay? It's a line that crosses the y-axis it goes all the way down at negative 3. Sorry, not drawn to scale. Negative 3, it's got a slope of negative 1. So this is actually negative 3 minus 1x. Sheesh, that's a little complex. I might adjust the homework on this, so if you're getting worried right now, don't be. All right, next example, 27. Nah, we're not going to talk about that one. Oh, I wanted to do every single one of these examples. Just bottom line is, 31. If you check out 31, I just want us to have a sense for what the graphs look like. So x squared plus 4, it's a pretty basic parabola. Remember quadratics, parabolas? Well, if you're just adding 4 to a parabola, it's 4 units shifted up that creates that shape. Now, what I wanted to get across on this is, when you take the absolute value of a parabola that's always above the x-axis, when is the output for this graph going to be negative? When is it below the x-axis? It's never below the x-axis. So saying that we need to take the absolute value of x squared plus 4 is an unnecessary statement. It's just like, I don't need the bars. It's always going to be something squared, positive number, plus 4, another positive number. So it's the same as x squared plus 4 without the absolute value bars. All right. All right, I'm going to check out a few in the next section that are really, really just out there, kind of like think piece type problems. Again, this is textbook language working its magic. So when you see number 33, it says replace the little box in between them with a symbol equal to or not equal to make the resulting statement true for every single number A, B, C, D. So it's like saying it's got to work for any numbers you plug in there. So what we could do is start just randomly assigning values to A, B, and C, and seeing if we plug in on the left, it matches with a plug-in on the right. For instance, I could say like, hey, let's let A equal 4, B equal 5, and C equal 6. And well, make D equal 7. And we can just plug those numbers in everywhere we see an A and a B and a C and a D. And if they match up, maybe it works out. That seems too time consuming to me. What I want to do is evaluate, do I see any patterns here that might be helpful? And you see, I took a textbook where people were plugging in numbers. You can kind of see the fate values of them plugging in the numbers. First thing I notice on number 33, all right, is you've got AB plus AC divided by A. Did you guys know you can factor the A on the top out? And then when divided by the A on the bottom, they cancel each other? Wow. Okay. So it's really saying what's going on between B plus C, right? That's what you get, versus B plus AC. So it's not true for all real numbers. I mean, the only number it works for is if C is 0. I mean, if C is 0, it's like, they work, but it's got to be true for all real numbers. So this one is not true. Or not equal to, whatever you want to say for it. All right, I wanted to explore 35, 37, 39. Yeah, let's do it. So when you look at number 35, it's kind of a similar situation. They're saying like, hey, you got B plus C over A and B over A plus C over A. I just want to see if I can make the two match up as variable expressions. So when I see the right-hand side, it's like, hey, they have common denominators. You can just straight up add the numerators of a fraction whose denominators are the same. So the right-hand side should be combined as B plus C all over A, which is exactly what the left-hand side is saying. So on the left-hand side, you just say, yeah, it's equal, always. All right, for 37, they're asking if A divided by B divided by C is the same as A divided by, and then they put B divided by C in parentheses. I'm going to come over here and expand that out a little bit. So here's A divided by B in parentheses, divided by C. And then I've got, I'll put it below. A divided by parentheses C divided B divided by C. So I want you guys to just think, try to think intuitively on this. So before you check it out, ask yourself, do you think they're the same thing? Pause the video and do that. All right, unpaused. Why don't we just rewrite them as fractions? This is A over B, and then you're dividing C. This is A divided by B over C. I'm just putting the expressions that are in parentheses as fractions. And you can do that because that's what division is. Division is the same thing as making fractions. So then, quick review, how do we divide fractions? Well, I got a fraction divided by a whole number. Let's make that a fraction. Flip the second and multiply. Yeah? So I flipped C over 1 and made it 1 over C. That will give us A times 1, 1A over B times C, BC. That's what we get right here. So hopefully I didn't go too quickly on the rules of fractions. It's kind of like we learned it back in pre-algebra days, but maybe we've kind of forgotten it, gone soft on it. This shows that we understand it completely. Over here, I'm going to take A and put it divided by 1, then flip the second and multiply. So A over 1 times C over B is really what's happening here, which gives me AC over 1B. Whoa! No. They are not the same. So you'd put this situation, they are not equal to each other at all. No. All right, on the last one, number 39, all they did was a little factoring trick. A minus B over B minus A. What they did here was they said, what if we were to say on the bottom, positive B minus A, what if we took that negative out, we factored it out? So factoring is just the reverse of the distributive property. It's dividing out a negative 1 from both parts here. So you're just taking the negative 1 out, which means the A is now negative over negative, positive. The B is now a negative 1B. A over B cancels with A over B. So that's 1 over negative 1. It equals negative 1. So that one equals. Part 3 coming up shortly.